Thanks for having me here. So today I'm going to talk about work done in collaboration with Shivaji Sondhi on, as Anusha preempted, phases of driven quantum matter. So perhaps a central goal of quantum condensed matter is to characterize the different possible phases of matter. And when we characterize the different phases of matter, phases are characterized by the long-distance behavior of their correlation functions. And so in the equilibrium context, when we talk about classifying different phases, we're talking about characterizing the different possible long-distance correlation behavior in these in such settings. And when we talk about phase transitions, across a phase transition, the long-distance character of the correlations changes sharply. With many-body localization, a new notion of phase has arisen, the notion of an eigenstate phase and eigenstate phase transitions. And so within a particular eigenstate phase, all of the eigenstates of some many-body Hamiltonian have some common feature. And across an eigenstate phase transition, this common feature experiences a sharp change, even though perhaps thermally averaged or thermodynamic quantities are smooth across such a phase boundary. So both of the problems that I mentioned above, the equilibrium thermodynamic problem and the MBL eigenstate phase problem, involve characterizing the eigenstates of local time-independent Hamiltonians. And so what I'm going to be talking about today is asking the question of what types of new phenomena can arise in systems which have time-varying Hamiltonians. Is there even a sharp notion of phase of matter for a driven system? So I'm mostly building on work by Vedika Kamani and my collaborator Shivaji Sondhi in 2015. We examine periodically driven systems. So these are systems whose many-body Hamiltonians are periodic functions of time. So h of t is equal to h of t plus big T. There's Floquet period t. What they found in that paper, which was mostly numerical, was that provided the Hamiltonians involved in, provided this family of Hamiltonians have sufficient disorder, you can in fact have a sharp notion of phase of matter for these periodically driven systems. So what do I even mean by a Floquet phase? Well, within a particular Floquet phase, all of the eigenvalues of the so-called Floquet unitary have some common feature. The Floquet unitary is time translation operator for one period, one big T. So you can see it's just the time-ordered exponent of the Hamiltonian over a Floquet period T. So the game of characterizing Floquet phases is, I'm saying, the game of characterizing the eigenstate properties of these Floquet operators. Similarly, you can have a notion of phase transition between different Floquet phases. So within a Floquet phase, all of the eigenstates of this operator have some common feature, and across a phase, upon tuning some parameters in the Hamiltonian, you might find that those properties have a sharp transition. And that's what a Floquet phase transition means. One thing to mention here is that disorder really does seem to be a necessary component in this story. And if you take systems which are translationally invariant and you periodically drive them, they generically heat up to infinite temperature. By that I mean if if you take a system with a translation invariant Hamiltonian and you kick it periodically, the correlations after long times end up becoming thermal in infinite temperature. That's if you have a clean system. If the system is disordered, and this is the situation I'm going to be discussing today, the disorder seems to disrupt this heating mechanism. So with that as sort of background, let me just summarize the main things that we do in this work. So building on this idea that there's a sharp notion of phase of matter for these periodically driven disordered systems, we present a whole new class of disordered analogs of known symmetry-protected phases in 1D and a classification scheme for these. And something I want to emphasize is that many of these new phases can only arise in driven systems. So by that I mean these new Floquet SPT phases have eigenstate properties that you can't realize in systems with just a Hamiltonian that doesn't vary in time. These phases are intrinsically driven. So that's a classification of SPT states. We also have an accompanying classification of symmetry-broken phases. So these are phases which, for instance, have kind of long-range order in their Floquet eigenstates. So we also have a similar classification for symmetry-broken states, and we find a whole new class of symmetry-broken states, which also can only be realized in systems with Hamiltonians that vary in time. So let me just give you a general overview of what the SPT classification scheme, how that works. So the input for the SPT classification scheme is some global symmetry group G, which we take to be a finite group and abelian, and a family of time periodic Hamiltonians which respect this symmetry. And we're going to be examining the properties of this Floquet unitary UF. So I'll use this. So we're interested in time-varying Hamiltonians which are such that this Floquet unitary UF has a complete set of conserved quantities, which I'll occasionally lapse into calling L bits. So there's a full set of local operators which commute with UF and which form a complete label, a complete set of labels for the eigenstates in the system. So that's what I mean by complete set. So with this symmetry assumption, the locality of H, and this assumption that UF has a complete set of L bits, we ask what properties, what eigenstate properties of this Floquet unitary are robust to small perturbations to the Hamiltonian in the bulk, which respect the symmetries of the problem, and arbitrarily large perturbations to the Floquet unitary at the edge, provided those perturbations respect the symmetry. Yeah?
So why the restriction to abelian?
That's an MBL assumption. So if you try to write down so let's go back to the equilibrium problem. If you try to write down a Hamiltonian which is an SPT but which has non-abelian symmetry group, you find that there are necessarily some sort of degrees of freedom which are not completely fixed by the projectors for that SPT Hamiltonian. And the idea is that those are supposed to disrupt those can actually behave like a bath and lead to an infinite temperature heat up. The more mundane reason why we didn't treat those is because I couldn't get the proofs to work in those cases. So what proofs? Yeah. Okay. Okay. So with that stuff as input, the symmetry stuff, and this assumption that there's this complete set of L bits, we argue that the Floquet unitary can always be brought into a sort of generic form. You can shuffle around the operators so that it always looks like this, e to the minus if VL VL, where f is some local functional of the conserved quantities in the bulk. So it looks something like a standard local MBL Hamiltonian. And these VL and VR operators are unitaries which are localized to the left and right ends of the system, but which commute with all of the local conserved quantities in the bulk. So we argue you can always bring it into this kind of form. And so the output from all of those assumptions and this technical step is that there's a classification for these Floquet SPT states which has two independent parts. The first part, this CL of G, CL for classification of G, is just the usual SPT classification for this MBL Hamiltonian F. The second part of the classification I call AG, and that just characterizes the way in which these VL and VR operators commute with the global symmetries in the problem. And it turns out that that's the full set of data which tells you what the spectra of these Floquet drives look like. So it's a two-part classification. So let me give some examples and show you what some examples of classifications look like. So let's go to 1D and consider 1D superconductors which have no symmetries other than fermion parity. So that's class D. So in the undriven setting, the equilibrium undriven setting, there's a Z2 classification for such states. One of these states is the famous Kitaev wire state with Majorana N modes, and the other state is just some trivial featureless boring superconductor with no protected edge modes. So there's a Z2 classification because there are two possibilities for SPT order in such systems. In the Floquet setting, we find that there's a Z2 cross Z2 classification. And this mirrors that general form for the classification I put on the previous page. The first bit, this Z2, is just the Z2 corresponding to the usual undriven classification. And the second part tells you something about those VL and VR operators that I spoke about on the previous page. In fact, in the present case, this red Z2 tells you whether those VLs and VRs are fermion parity even or fermion parity odd. Turns out they're either fermion parity even or fermion parity odd, and that's something that we show. Okay, so let me give you a more exotic example. If you take that 1D superconductor and you insist on having time reversal symmetry with T squared equals 1, in the undriven setting, there's a famous interacting classification, which is the Z8 classification, which is, amongst others, due to Kitaev and Witkowski. In the Floquet setting, we find the number of possible phases as quadruples. So again, the first part of the classification is the Z8, which is just the Z8 from the undriven classification. And the second part is the Z4, which tells you how those VL and VR operators commute with fermion parity and with time reversal symmetry. Turns out there are 4 possible options in that case. So this is a completely new set of states. Okay, and for people who know stuff about cohomology, just flash up some sort of general results on G, abelian finite, and bosonic. You can see for bosonic finite group cases, you get this sort of structure H2 cross H1. In fact, you can think of this as coming from a Kuhn formula, if you're into that. But if you don't understand the symbols on this page, just ignore this page. Okay, so for the remainder of the talk, I'm going to try and illustrate some of these sort of general high-level ideas with a very explicit example. So I'm going to look at the class D case in gory detail and show you how this Z2 cross Z2 classification comes about in that case. And then I'm going to provide explicit examples of Floquet drives realizing the C2 cross C2 order. So I'll try and be as pedagogical as possible. So I'll start with just talking about the basics of the Kitaev SPT in 1D, where we talk about properties of the ground states of Kitaev-like Hamiltonians. Then I'll introduce the many-body localized variant of this Kitaev SPT. So that's when you take your Kitaev Hamiltonian and Kitaev wire Hamiltonian, and you introduce interactions and strong disorder. And it turns out that if you do that right, the entire spectrum of the resulting Hamiltonian has these edge Majoranas and some vestige of the SPT order hidden in it. And so using some of that technology, I'll explain the Z2 cross Z2 classification, give you some examples, and then I'll briefly mention these symmetry-broken phases, which I alluded to before, and their connection, their recent connection to this idea of time crystals. So, okay, so as promised, let's start out with the SPTs in 1D, the Kitaev chain. The Hilbert space for the models we're considering consists of an on-site spinless fermion degree of freedom, F dagger. We'll find it convenient to split F dagger into 2 Majorana degrees of freedom. So these Majoranas square to 1, but they're fermion parity odd operators. And the connection between the 2 sets of operators is given by something like this. So we're going to consider Hamiltonians with only fermion parity symmetry. So fermion parity means you go to every site and you multiply an operator which is -1 if there's an odd number of fermions there and +1 if there are an even number of fermions there. And in the Majorana language, this has quite a simple expression. So with these symmetries and with this setup, there are 2 qualitatively distinct SPT orders with this fermion parity symmetry. The first one is a very boring, featureless-looking superconductor, and I'll call it throughout the trivial state Hamiltonian. And an example of a Hamiltonian which has this trivial order is this guy. So this is just a sum over all sites of on-site fermion parity operators. There, psi r bar. So one thing to note about this Hamiltonian, and I've chosen it very specially so as to make the generalization to MBL as simple as possible, is that it has a complete good set of local conserved quantities of the motion. So these psi r bar operators all commute amongst themselves, and they all commute with the Hamiltonian as well. And indeed, they form a complete set of labels for the Hilbert space of the problem. a complete set of good quantum numbers and good labels for the problem. And you can see the ground state of this Hamiltonian has all of these gamma r's equal to 1, because that's what's enforced by this Hamiltonian, minimizing that Hamiltonian. In contrast, the Kitaev state has a slightly different toy model Hamiltonian. It looks something like this. It looks quite similar, but it involves couplings between Majoranas on different sites. It also has a good set of local conserved quantities of the motion, but they look slightly different. They involve Majoranas on different sites. And the ground state is, again, gamma r equals 1. But there's a difference here, because while on a system without boundary, these are indeed a good set of labels for the state, on a system with boundary, you can see that if you fix all of these gamma r's in the bulk, Majorana degrees of freedom at each end are actually left undetermined. And so this is the principal difference between the Kitaev and the trivial state. And so let's just see this in action again. You know, if I take an open chain and I fix all of these degrees of freedom, then okay, I know what the state is. It has some number of fermions on this side, some fermion parity on this side, etc., etc. Whereas in the Kitaev case, if I fix all of these L bits, I have this dangling Majorana here and this dangling Majorana here. And these dangling Majoranas are associated with a protected spectral pairing. By which I mean, so fermion parity P is a commutes to the Hamiltonian. That's input. They're all fermion parity odd. Psi1 bar also commutes to the Hamiltonian because it doesn't appear anywhere in the Hamiltonian for the Kitaev state. But psi1 bar and P anti-commute with one another. The upshot of this is that if I have some eigenstate of both fermion parity and the Hamiltonian, which I can write EP, then psi1 bar of EP has the same energy because psi1 bar commutes to the Hamiltonian, but opposite parity because it anti-commutes with fermion parity. And so this tells me if I write down the spectrum of the model, if I have an eigenstate here, I'll have an identical but orthogonal eigenstate at the same energy. So there's a spectral pairing. So another more highfalutin way of saying basically the same thing is to say that the trivial state and the SPT state are distinguished by the manner in which fermion parity acts locally at each edge. This is something that's sort of said a lot in the literature. What it means explicitly in this case is if let me show you what it means in the trivial case. So if we have a model which has a set of L bits and we fix the L bits in the bulk to be some prescribed values, we're asking how fermion parity acts in that subspace of the Hilbert space. For this trivial case, fermion parity restricted to some subspace where all these L bits are equal to some values actually just gives you some scalar, because fermion parity is just a product of these L bits. All of these L bits are some scalars, so this is just some scalar operator. In the Kitaev case, it's a little bit different, because if we fix all of the L bits in this case take a different form, we can end up simplifying this product to something which involves a fermion parity odd operator, psi1 bar, acting at the left edge, and a fermion parity odd operator acting at the right edge. And so this, more generally, is the thing that will distinguish these two phases as we tune away from these special points. In the trivial phase, fermion parity will act like an even operator at the left edge and an even operator at the right edge. In the Kitaev cases, the fermion parity will act odd at the left edge and odd at the right edge. Odd at the left edge and odd at the right edge as well. So the models I've looked at, and I guess I sort of preempted this with what I was saying before, but the models I've looked at so far are completely finely tuned. They don't have any interactions in them, and they are translationally invariant. But in the presence of disorder, and even in the presence of some interactions, many of the above statements can appear to continue to hold. There's no proof that they continue to hold, but numerics suggest they do, and there are various theoretical hand-waving arguments suggesting that they do. So what properties am I talking about in particular? Well, this property that there's a complete set of local conserved quantities in the bulk, and that fixing these local conserved quantities in the bulk, P restricts as either PL, P restricts in this way, and PL and PR are either even or odd. Okay, so what I'm saying is that as you tune away from these special points, there's this sort of notion of an eigenstate phase where all of the eigenstates of certain classes of Hamiltonian have a fermion parity even restriction to each edge, and all of the eigenstates in another class have a fermion parity odd restriction to the edge. Okay, so all I was trying to say here is that in 1D systems with fermion parity symmetry and strong enough disorder, there are two types of stable eigenstate phases distinguished by the way in which fermion parity acts at each of the edges. And the more general statement is that for certain SPTs, there exists stable disordered variants of these SPTs, which are eigenstate phases. And within those eigenstate phases, you can say that the symmetry factorizes in a particular way onto the left edge and onto the right edge. And the way in which the symmetry factorizes is characterized by a co-cycle or projective representation, something like that. Well, exactly that, and extra data about fermion parity in fermionic systems. So now what I'm going to try and do is apply some of the same technology to driven systems. So let's take as our input a time periodic Hamiltonian with fermion parity symmetry, which is local. And let's assume that H is such that UF has a complete set of Hilberts in the bulk, such that when you fix those bulk Hilberts and ask how fermion parity acts, it acts like this, and this PL operator is either even or it's odd. So we're assuming that, so from the outset, we're assuming that UF, that the spectrum of UF looks very much like an SPT spectrum, in that the symmetries factorize in this particular way on the edges. So, I mean, it seems like we've given up the game there. We've assumed rather a lot. And you might have thought that actually that completely fixes the spectral properties of the Floquet unitaries, but it doesn't. So this is where this technical lemma comes in, where we argue that UF can be decomposed in this way, where F is just some function of the local conserved quantities mentioned, and these VL and VR operators of unitaries localized at the left and right edges of the system respectively, which commute with all the bulk Hilberts. So, in fact, it turns out that VL and VR can have some properties which are protected, and which lead to different types of spectral properties at the edges. Yeah, and just another thing, notice that UF is acting very much like any other symmetry in the problem, in that when we restrict it to some subspace which has prescribed values of the Hilberts, it factorizes into some operator that acts at the left end of the system and some operator that acts at the right end of the system. Okay, so now let me just sort of show you an example of a kind of argument which shows that these VL and VR operators are either fermion parity even or fermion parity odd. In the more general cases, it's always some kind of variant of this kind of argument. So we know that P commutes with UF. Okay, and it turns out that P also, via some, I guess, it turns out that for all the examples we can solve exactly, P also commutes with the Hilberts, and there's it's not a precise argument, but there's a good argument to say that it continues to commute with the Hilberts away from the fixed point. So using that information, we can turn this equation into the statement that P VL VR P is equal to VL VR. Now, P, fermion parity, is some local circuit. It's just a product of operators on different sites. And so P on VL is, again, some operator that's localized at the left end of the system, and it's a unitary, so we can write it in this way, as VL, again, times some other operator that's localized at the left end of the system. Similarly, we can make a statement about VR, which shows us that we can write it this way. And if we substitute this back into this equation over here, it immediately implies that theta L, theta R is equal to 1. So theta L is some operator that's localized at the left end of the system, and theta R is some operator that's localized at the right end of the system, and yet they're inverse to one another. So the only way you can get this to happen is if both of these are phasors, pure phasors. So it turns out that this implies that this is of this form. Call it something else, phi times the identity matrix. But then it turns out that because p squared is equal to 1, you can show that this phase over here is either plus or minus 1. Okay, and so these VL and VRs are either even or odd. And it turns out that that's the only sort of protected property of these if you end up perturbing your unitary, provided you do it symmetrically. So what data do we end up getting from this? Well, some of the input was the parity of these PL and PR operators, which told us whether the bulk of the model looks like a Kitaev topological order or a trivial superconductor. So that's some Z2 index. And the second bit, which we worked out, was the parity of VL and VR. And so that's a second Z2 index. And it's the combination of these two Z2 indices which give us the robust spectral properties of this model. The first Z2 we already knew about. The second Z2 we figured out. There's also a kind of physical interpretation behind all of this, which is that if you have a Floquet unitary with the various assumptions I've put in, you can always put it into this form. And so what does this mean? This means you sort of hit the system on the right, you hit the system on the left with something, and then you evolve the system with like a constant Hamiltonian f for time 1. Okay? So now if VL and VR are fermion parity odd, what this operator really does is it tunnels a Majorana from the right edge of the system to the left end of the system, and then evolves for a constant time. So you can actually think of all of these as kind of a combination of a constant time evolution and a pump, which pumps some sort of charge around the system, which is, nice anyway. So now I'll construct some examples of each of the drives. And the drives I construct we call binary drives, because they just involve two Hamiltonians. The Hamiltonian which we will use to define the drive is a time-varying Hamiltonian, which for some time t0 will be h0, and for some time t1 will be h1. Okay? So we bang with one Hamiltonian and then bang with another, and we end up getting a Floquet unitary that's of this form, right? And the H0 is just going to be the trivial Hamiltonian we had before, and the H1 is going to be the Kitaev Hamiltonian. So I'm going to show you how these different Z2 cross Z, the four different possible phases come about by choosing different values for T1 and T0. Okay? So let's do the boring examples first. So this is the unitary we're looking at. And first of all, I'm going to set T1 equal to 0, so this term disappears. And in that case, and I'm going to set T0 equal to 1. So in that case, the Floquet unitary just looks like a evolution with the Hamiltonian H0 for time equals 1. So that means that the eigenstate properties of UF are actually just exactly the same as the eigenstate properties of H0. If you diagonalize H0 and you know what the eigenstates look like, then you know what the eigenstates of UF look like. In the second case, we're going to switch T0 off, so cross out this term, and just evolve with this guy for time equals 1. In this case, the spectral properties of UF are the same as the properties of H1. H1 was the Kitaev Hamiltonian, so it has this pairing in its spectrum. So for this guy, we will have the same spectral pairing as in the Kitaev state. The eigenvalues of U live on the unit circle in the complex plane, because it's a unitary. And in this second drive, we're going to have, double degeneracies. So if there's an eigenstate here with unitary eigenvalue U and parity P, then it has a friend at exactly the same eigenvalue of the unitary, but a different value of the parity. So we get this sort of doubling, okay? All right, so these are the two trivial examples. Let's do some examples which are sort of intrinsically driven. So for these, what we're going to do is drive this Hamiltonian. It looks bizarre at first, but you drive this Hamiltonian with T0 equals pi over 2, and this Hamiltonian with T1 equals 1. Okay? And what I'm going to show you now is that with those parameters, you can massage this unitary into this kind of form. So let me just show you how that works, just in terms of the algebra of it, so that you aren't suspicious that I'm trying to lie to you. So the crucial identity that we're using here, in fact, is that So here's my H0 and H1. If I look at this guy and evolve it for time pi over 2, I can turn this, if you look at the form of this guy, into some product of sites R of e to the I psi r bar, pi over 2. All of the terms of the Hamiltonian commute, so you can pull the exponential apart. This guy, just by Taylor expansion of this guy at time pi over 2, is in fact just equal to I psi r bar. Sorry, there's actually a second I in here. Something like this. Okay? So you can turn this guy into something, I'm not going to keep track of phases here, but something that's proportional to this guy. Okay? Let's do this on a system with boundary. Okay? This, in turn, we can re-express as I psi 1 bar psi n product over r equals 1 to n minus 1 of I psi r plus 1. Okay? I've taken out, basically this guy contains all the Majoranas in the system. I've taken out 2 of them and then reordered this product. And this guy, in turn, can be rewritten as psi 1 bar psi n e to the minus I pi over 2 times h1 using this same exponential identity. Okay? Okay, so you can reorganize this unitary, and basically you end up getting rid of this term, absorbing most of it onto h1, so that's what shifts this by pi over 2, and then multiplying it by some operator at the left end of the system and some operator at the right end of the system. And so you can see here that except for these operators at the edges, the bulk properties of this guy are just the same as the bulk properties of h1. So in the bulk, this looks like the Kitaev state. But now there are these 2 fermion parity odd operators at each end of the system. And in fact, their presence leads to an interesting new type of spectral pairing. Because whereas previously, so let's look at the Hamiltonian that we have now. So we've evolved this guy for some time t, h1. We have psi 1 bar psi n. Now, psi 1 bar commutes with h1. Okay? Because that's one property of the Kitaev Hamiltonian that we're using. This guy is equal to 0. So you can see that if you try and move psi 1 through this expression, it'll move readily through h1, but it'll anti-commute with the psi 1 bar psi n. Right? And so this psi 1 bar operator, we know 2 things about it. It anti-commutes with UF, and it anti-commutes with the fermion parity. These 2 facts can be used together to show that if I have an eigenstate with with UF eigenvalue U and parity P, then psi 1 on this guy behaves like something with these eigenvalues. This bit comes because it anti-commutes with UF, and this bit comes because it anti-commutes with P. So it's qualitatively distinct spectral pairing to this case. So this was like a trivial case where we just evolved with H1. In the present case, the spectral pairing looks like, if I have a state here, then it has a partner on the other side of the circle. It's an awfully drawn circle, sorry. Okay, so states are... So you can see that whereas before things were coming in degenerate doublets, now they're coming in doublets which are actually at different values of UF eigenvalue. Okay, so there's a qualitatively different kind of spectral pairing in these models. For the last example, I'm not going to go through it in the same detail, but it's basically the same thing. If you evolve with T0 equals 1 with the trivial Hamiltonian and T1 equals pi over 2 with the non-trivial Hamiltonian, you can massage UF into similarly, using the same sort of procedure. And in that case, you find that there's a spectral quadrupling. So if you have some state with eigenvalue U and P, then you have one at U at minus P, minus U at P, and minus U at minus P. And in fact, you can form a phase diagram of all of these. So this is a phase diagram tells you what the eigenstate properties are as a function of T0 and T1. These were the trivial drives. This is the non-trivial drive that we looked at in some detail, and this is the spectral quadrupling drive that I just alluded to briefly. And so the really surprising thing, and we really need numerics for this statement, is that if you introduce disorder and strong enough disorder and interactions, that the statements that I've just made continue to hold. That you still have spectral pairing. This time they're only protected up to exponentially small degeneracies and exponentially small corrections in system size, but they continue to hold, and that's what numerics suggest. And we sort of have a theory for why this is happening, which I described before. Okay, so what we did was I argued the Z2 cross Z2 classification of class D and constructed explicit drives. So let me say what we do in general. In general, we do pretty much the same procedure for any finite abelian symmetry group G in 1D, including those with time reversal. The procedure with time reversal is a bit more complicated, but actually compensatingly more interesting. And our classification takes this product form, which I alluded to at the beginning, where the first part is the undriven classification, and the second part tells us how these VL-VR operators commute with the symmetries in the problem. In fact, there's another way of looking at all of this, which where you view time translation as being the same as any of the other symmetries in the problem. And you consider looking at cohomologies of groups of the form G, where G is the global symmetry group, and time translation, which you can think of as Z. So that's another way of getting the same results. Okay, so let me just briefly discuss the symmetry broken states. So if we go back to the equilibrium setting, what are the different types of eigenstate orders we can get in 1D? Well, we can have SPTs, and we can have spontaneously symmetry broken orders, and we can have things that are kind of in the middle between the two, which I won't talk about. So in the last part of the story, I'm going to, we focused on the SPT story, and now I'm just going to give you some results on the spontaneously symmetry broken result and just highlight some recent connections to time crystals. So let's just consider drives with periodic Hamiltonians. So we're going to consider Floquet unitaries, which have a completely spontaneously broken discrete symmetry G eigenstate order. So for instance, for the rest of this section, I'll just talk about G equals Z2, because it just makes it a bit more concrete. So what I'm saying here is I'm going to consider Floquet unitaries with just Ising spin glass eigenstate order. So each of the eigenstates has long distance Ising spin glass order. So in pretty much the same way as I did in the first part of the talk, we classify the Floquet unitaries for such systems. And in the Z2 case, we can reduce those Floquet unitaries to one of two forms. One of the forms just looks like a constant time evolution with a spin glass Hamiltonian, and the other one looks like a constant time evolution with an Ising spin glass Hamiltonian followed by a global Ising flip. I'll show some explicit examples of what these look like on the next page. So let me just consider idealized examples of those. So the first unitary I mentioned, just constant time evolution with something like this, where J is random. Okay. Its eigenstates just look like cat states. And the arrows I draw now will be Ising spin configurations. So the eigenstates of operators that look like this just look like the following. So these are sigma Z configurations. Okay. And if I look at the spectrum of such a Floquet unitary, I'll find again that there's a spectral pairing. So if I have one cat state at this energy and some value of the Ising flip operator, then it'll have a partner at the same Floquet unitary, but with negative the Ising flip operator. Because you can see that the Ising flip on the plus option here gives you +1, and the Ising flip on the negative option gives you -1. So I'm saying that these two states for this unitary are exactly degenerate. And they're distinguished only by the global Ising flip operator. So now let's contrast that with the spectrum of the second type of operator, which involves evolving with this guy and then hitting the state with an Ising flip. A guy that looks like this. So for this guy, in fact, the eigenstates look exactly the same, but the quasi-energies are different. And again, they're pi split. So if you have one cat state here with unitary value here, and Ising flip operate and Ising value this guy, then you have another guy at minus u with this guy. So in terms of cat states, this guy is, this guy, and this guy is this guy. Okay. So you can see again, in this case, the spectral pairing is distinct to the spectral pairing that we got in this case. Okay. And so what I was saying on the previous page is that even as you move away from these exactly solvable fixed points, some sort of statement of this form continues to hold, provided you don't break the Z2 symmetry. And all Floquet unitaries of this form can be reduced into one of these two forms. So let me just briefly say, why some people might say this is a time crystal. And this is related to recent work that Station Q released, Chetan Nayak and Dominic Else, which is a very interesting paper, which you should read, which is, if I look at that first unitary and I look at the dynamics of the Ising order parameter, if I conjugate sigma z by this operator, the sigma z's just move through and this guy stays constant in time. And a similar statement to that will hold if you perturb away from this exactly solvable model. The second unitary, however, flips the Ising order parameter. So if I evolve this guy for n Floquet periods, this guy keeps flipping up and down, like this. And so you might say it's a time crystal insofar as the Hamiltonians for the models that we use to construct these drives have this sort of symmetry. But the natural order parameter for the problem does not. Sorry, I should have a t here. T. Should be a t, not a 0. So the order parameter doesn't have the same symmetry as the Hamiltonian. And this is actually pretty close to a definition of time crystal that Oshikawa and Watanabe, I think, put forward in 2014. But they were sort of looking in the equilibrium context and weren't thinking about MBL. And were thinking about spontaneously breaking continuous time translation symmetry. Here I'm thinking of spontaneously breaking a discrete time translation symmetry. So it's distinct in that way, but kind of similar in spirit. Let me just say that, more generally, we can look at spontaneously symmetry broken drives, and we have a more general classification for all of these. It turns out that if you look at a symmetry group G, which is completely spontaneously symmetry broken, you look at that type of eigenstate order, there are in fact Z of G different types of Floquet phases with that symmetry, where Z is the center of the group in question. So that's what we find. Okay, so that's the end pretty much. So building on this idea that there's a sharp notion of phase of matter for periodically driven disordered systems, we put forward a classification scheme for abelian SBTs in 1D with finite group G. And these guys have spectral qualities which we can't realize just using time-independent Hamiltonians. And we have a similar classification for spontaneously symmetry broken states. Last thing I'll mention is that there are a number of existing proposals for measuring MBL systems in experimental scenarios, and we've done a basic check that these can be readily generalized to these Floquet states. So maybe someone can actually measure this type of behavior someday. Okay, so that's it. Oh, wait. So here are the two archive references, and these are some papers which came out shortly afterwards, and their results overlap with ours in certain places, and we all seem to agree where we overlap. And this is this work on time crystals that I mentioned. So that's it.
Okay, maybe I'll ask one. A lot of what you said was in 1D.
Yeah.
Is that somehow intimate to how you can prove things, or do you think the same? It is because there are classifications in higher dimensions for it.
Yes. Yeah. So actually, the generalization. Okay. The reason we focused on 1D is because it's the only place we really believe that MBL must definitely exist, and that seemed to be a crucial thing for talking about these states. This generalization, And the way that we arrived at the result is not immediately generalizable to higher dimensions. Subsequent paper to ours wrote it down in a far slicker way, where you can think, if the classification in the undriven setting for, let's say, just bosonic symmetry group G is this guy, finite bosonic symmetry group G is this guy, cohomology or something, then you can re-express all of our results as this sort of thing. At least when D is equal to, all of our results agree with this sort of thing when D is equal to 2. So the idea here is that this is the symmetry group in the problem, and this is time translation. So you literally just put that into the cohomology framework. So, once you see that what we're doing is equivalent to calculating this thing, this makes it rather more easy to generalize it to higher dimensions and start fiddling with D. So I think the math certainly does generalize to higher dimensions. The simple physical interpretation in terms of pumping charge doesn't. But yeah, so in principle, in high dimensions, these also exist. I think the simplest example I found was something like G equals, I might be misremembering, Z2 cross C2 in D equals, just in D equals 3. That, I think, gave me a non-trivial answer for this guy, I think. Okay. Yeah?
So about the classification of symmetry breaking for driven systems, I wonder whether there is an analog for a classical system.
An analog of spontaneously breaking this time translation symmetry.
It's going to define the world evolution.
I haven't thought about that, but yeah, I mean, like if you're just thinking about this, well, actually, hang on a second, because okay, so in some sense, taking the classical limit is like taking the on-site Hilbert space number of degrees of freedom to infinity. Like instead of considering Ising spins, we consider rotors, right? So okay, I can think about spin halves as being some rotors with some sigma model term, right? Yeah. But the problem is with when you have rotors on site, or like that's like an unbounded local Hilbert space, and such systems are not believed to be stable to. So such systems are believed to heat up to infinite temperature, I think. But although I guess you guys did your ON thing, is that yeah? So I think that such systems would eventually maybe I'm guessing would become chaotic. But maybe you actually have a better answer than that.
I think it's just we don't know.
Or you just don't know. Okay. The expert says we don't know.
Yeah.
So.
So maybe you could say a bit more. Are there are there other examples, classical or quantum, where the time transition is broken spontaneously?
I'm actually very new to this time crystal thing, so none that I know of that didn't have. So I mean, Wilczek came up with these various examples of time crystals, but as I understand it, there are various problems with those earlier papers. So I have not gotten to the technical details of that, so I'm unable to comment either way. But I mean, the Watanabe paper, so they put forward a definition of time crystal and then showed that they didn't exist. What we're doing is slightly modifying that definition, and then that picture, these are time crystals.
But they showed that you cannot spontaneously break continuous time transition.
Yes, that's right. Sure? That's right. But I haven't thought about discrete, and I'm not sure if anyone else has thought about discrete until now. Anyone else? All right.
If there's no more questions, it's time for the speaker.